So you have a lever AB, right, which is hinged at C. So it is attached to a control cable. So when I say cable, it means so tensile force or tension force is acting on this. Okay. So the lever is subjected to a 500 Newton horizontal force, which is mentioned here. So they are asking you what is the tension in this cable and what will be the reaction at this point C, right? Okay, before that, so we have to draw a free body diagram for this, right? So which one you have to draw as a free body diagram? The lever AB, yeah. So we have to concentrate free body diagram for that lever AB, right? So let me draw that part alone. So if I consider here, you will have something like this. This is my lever, right? This is my lever. So this is my point A. This is my point C, and this is my point B. Right? This lever is as these 3 points. So I am going to draw a free body diagram. So you know that there is a cable which is attached with respect to this, which means you will have a reaction here, right? You will have a reaction like this, which is T A to D. So TAD, right? You have TAD, which is acting here. And you have a hinge support here. So whenever you have a hinge support, you will have two reactions that was also been discussed. So this hinge support will have two reactions, which is we will call it as CX, C suffix X, and C suffix Y. Indicating that you will have reaction in X direction, reaction in Y direction, right? So if I mentioned RX, RY, there will be lots of names. So better I will go for C. So the same location with respect to X, with respect to Y. There are two forces, right? And then you also have a horizontal force, which is 500 Newton, right? So this is my free body diagram. The next step is I have to resolve the force. Whenever I have an inclined force, I have to resolve into horizontal and vertical. Whenever I have an inclined distance, that also I have to resolve into horizontal and vertical. So these are the two things which is very, very important, which you have to concentrate, right? So, so if you look about your forces, all these forces are horizontal and vertical except this TAD. So TAD alone I have to resolve, right? So this one I have to resolve. Okay, right. So that is one part. Next, if I consider the distance, so this is okay, vertical, but this 250 has to be resolved. This has to be resolved, and this 200 should also be resolved into horizontal and vertical. Only if you do that, then we can take moment and we can solve the problem, right? Okay, so we got these things, right? So let us consider the same diagram, so somewhat in a bigger way, so that it is easy for me to resolve this, right? You see that this AB lever is 30° with respect to x-axis, right? So if I draw some lines, so you can able to see. So let me draw something like this, right? So this one and this one. So this is my horizontal, and we consider this as AX, sorry, AY, okay, because this is in Y direction. It's just a name, so I'm giving some name. That's it. Okay, so this is AY, and this is AX. Okay, so let's identify what is this AX and AY, right? What is this AX and AY? So AX will be, so this is 250 and this angle is 30°, right? This is 30°, right? In that case, 250 and this is adjacent side, right? So what you will get? You will get 50 cos 30, right? So this will be 250 cos 30, right? So that will be the value here. So 250 into cos of 30 So you will get around 216. Next, AY will be 250 sine 30. So this one, right? So sine 30 is around 125. Say that 125. So this is 125, right? Okay, I have converted these things. So this 250 I have converted. Next, I will concentrate on this 200. So this is also inclined, right? That is also inclined. Okay. So in that case, I will draw an horizontal line. So from C to B, my 200 is from C to B. So which means I have to draw horizontal line from C to B, vertical line from C to B, right? That's it. So this is my horizontal line from C to B, and this is my vertical line. So I will call this as B to dx and dy. So next, if I concentrate on by, right, again, there is 30 degree, right, by, you can able to see that it will be what? Sine, right, sine. So it's just 200 sine 30. So it will be 100. Like similarly, if I consider bx will be 200 cos 30, right? So what will be the 200 cos 30? 173.2. So I got this value 173.2, and this is 100. Okay, so now I resolved all my distances. One yet to go, which is your force. I would identify what is my distance or angle with respect to this force, right? So here comes the critical stage. So your force is from A to D. If I want from A to D, I need two distances, horizontal and vertical distance, right? With respect to A to D, right? So what is your vertical distance from A to D, and what is my horizontal distance from A to D, right? So in that case, so you can able to see here, if I consider my vertical distance, right, from A to D, it is starting from here, move up to this point, right? So which means I already resolved one of my value, which is 125. This 125 plus 250, right? 125 plus 250. What is the value total? It is 375. So you got 375 as a vertical distance, right, for this force. Next, horizontal distance. If I look after horizontal, it is 260, which we already identified, because there is a line here indicating that D point and C point is in the same vertical location. So 260. In that case, I can easily identify what is my angle, right? Easily I can identify what is my angle. So what I say angle theta, it's just tan theta. So tan theta is 375 divided by 260. You can identify what is the angle of theta, right? So it's a tan inverse of this, right? So what is the value of theta? Yeah, you are getting 60 degree. Okay, very good. So this is 60 degree now, right? Now I identified all my force. So all my forces are identified and everything is done. Okay. So only thing is I have to solve this, right? So I have to identify. I have to take a moment. I have to say that sigma f x 0, sigma f y 0, and the moment as 0. What I can do is I have this TAD, right? So TAD is horizontally 60 degree, right? TAD is horizontally 60 degree. Now, of course, this location and this location, right? So what I am drawing here, I am drawing a triangle indicating that. So you know some distances with respect to this. Okay. So the only thing is now I am going to equate it. So let me equate it. So let me say that sigma fx is equal to 0. I'm going to add all my horizontal force and I am going to equate it to 0. Right? What are my horizontal force? Let us go one by one. Start from this 500. 500 is opposite direction. So minus 500. Then you have Cx horizontal plus Cx. And this TAD, so when I resolve it, when I bring it to horizontal, what happens? It's a positive and your angle is decreasing. So it will be cos, right? So which means I can write as plus TAD cos 60 degree, right? So any other horizontal force, that's it. So these are my horizontal force. I will equate it to 0, right? So which means I can write this as an equation. What is my equation? So Cx, right? So cos 60 is 0.866. Sorry, cos 60 is 0.5, right? Plus 0.5 TAD plus 0.5 TAD is equal to 500. This is my first equation. Okay, so when I equate sigma fx0, I am getting like this. Okay, next we'll proceed with second equation. So sigma fy is equal to 0. If I put sigma fy is equal to 0, so there is no vertical force here, leave it. Horizontal is here, you have a vertical force, which is Cy. So Cy, right? And this one, when I resolve this, it is TAD sine 60, right? It is TAD sine 60. So what you will get? So it is negative because downward direction, right? So minus TAD sine 60. Is there any other force? That's it. So there is no other force. This is equal to 0, right? So in that case, I can write it as Cy is equal to 0.866 TAD. This is equation number 2. Now I am going to take moment. So where I have to take moment? So where you have maximum unknown force. So my maximum unknown force is at location C, right? So in that case, I am going to take moment at C. So moment at C, and I'm going to equate it to 0, right? Okay, so A, I resolve the two forces. So I'm marking the two forces alone. One is vertical, 0.866 TAD, and this is 0.5 TAD. Cos 60, right? So these are the 2 points. This is my point C. This is my point B. And this is my force, 500. Okay. So when I draw the line, so you can able to see that. So this is my line. So we have a horizontal distance of 125. Sorry, vertical distance of 125. Horizontal distance is 260. Similarly, I draw something like this, right? So your vertical is 100 and 170. So 100, 170. Right? Okay. So now I will take what is moment at C. So moment at C for this three forces, because C location CXEY will get cancelled because there is no distance. So force into perpendicular, that is your moment, right? So let me take moment for this one. So when I take moment, horizontal force, so the distance is vertical. A இருந்து C க்கு வரைக்கும் vertical எவ்வளோ distance 125. Rotation, it is rotating in clockwise. So minus. So minus, so 0.5 TAD, this value, force, into perpendicular distance. Distance is 125. Right? So this is over. Next, this one. So when you look here, this is rotating in anti-clockwise direction, positive. So plus 0.866 TAD into vertical force. Distances should be horizontal distance 260. Right? Next, 500. This one, what is your force? This is your force, right? So force is horizontal, distance is vertical distance, which is 100. Rotation, clockwise. So minus 500 into 100 is equal to 0. You will get TAD is equal to 401.4 Newton. Right? This is my value of TAD. So once I got into this value, then it is easy for me to find out the other values. Right? So what I can do, I can substitute in equation 1 and equation 2 to find out what is my CX and CY. Can you find out what is CX and CY? 299.3. Okay, very good. CY?
347.6, sir.
Okay, 347.6 Newton. Yeah. So that completes our problem. So, okay, a small difference in this. Okay, let us proceed with the next one. Yeah. So there are different types of loads. We will talk about different types of loads now and its importance and how to calculate, how to convert these types of loads. Okay. And then different types of supports also. Right. The first one is a point load. So whenever force is applied at a particular point, then we call that as a point load. Okay, so it will be always indicated in an arrow. So any force, all the forces are always a point load. So it is acting only at that particular point. Okay, so that is this part. Okay, so the point load is an important one. So which is somewhat easy. So whenever we solve any problem, what we will do is we will convert to this point load, right? So that it is easy to solve because all our problems are related to the point loads. Okay. Yeah. So something like this. So right, it is acting only at a particular point. Right. Okay. The next one is uniformly distributed load. Right. So for example, so we discuss something like keeping a book on a table or a laptop or a computer on a table. So when you look after the surface of this computer or book, whatever it is large. It is a rectangular type of surface, right? So, but what you do, we will convert it, right? We will convert it to a point load. We say that at the center of the book, the weight is acting, right? We will convert it like that, okay? So actually this book, whatever it is, that is a type of uniformly distributed load, okay? The load is distributed at every point, right? So if we cut that book, automatically the weight will cut accordingly, right? So a small portion of weight will be acting on a particular portion of the book, whichever you cut, okay? So usually when we indicate it, we will indicate this as W per meter, right? So we will always indicate it as, so W in Newton per meter, right? Force in Newton per meter. ஒரு மீட்டருக்கு எவ்வளவு நியூட்டன்? L meter அப்படி இருக்குன்னா W into L, right? So இங்க என்ன இருக்கும்? So L meter அப்படின்னா this entire force will be W into L. ஒரு மீட்டருக்கு W. So அப்ப L மீட்டருக்கு W into L, right? Something like that. Okay, that is your uniformly distributed load, right? So it is indicated like this. So always it will be indicated like this, or it may be indicated in a different way, something like this. So a rectangular type of way, showing an arrow like this. Okay, so this is also an indication of a uniformly distributed load, right? So whenever you have a load like this, right? So you can convert it to a point load. So how to do that? As I told you earlier, this entire load is acting at the center. So which means W into L is the total load, which will be acting at the center, W into L, at a distance of L by 2. In the distance of L by 2. So this is how you can convert it. Okay. So these are some applications of this uniformly distributed loads. Okay. So converting it, it's a W into L at the center, which is L by 2. Okay. Next is uniformly varying load. Right. So this is something like your load is starting from 0 and goes to a particular value. Right. This type of load we call it as a uniformly varying load. Right. It varies. It varies. Okay. So the symbol is like this. Again, this is also in W Newton per meter. Right. So consider this as a triangle. If I consider this as a triangle, area of the, so similar to this. So if I consider here, W is my height, L is my breadth. It is a rectangle. Area of the rectangle is the total load, which is W into L. Area of the rectangle, which is equal to W into L. Where it will be acting? Centroid of the rectangle. Centroid is at the L by 2. Centroid is L by 2. Right? This is what is indicated here. Similarly, this is also same. The triangle. So what is the area of a triangle? What is the area of the triangle? Yes. Half into?
Half into base into height.
Yeah, half into base into height. So height is W, right? Base is L. So half into W into L by 2. So that is my force. Half W into L. So half into W into L. That is my force. Where it will be acting? Centroid of my triangle. Centroid is your, if I consider the centroid of the triangle, it will be acting at 2/3 of L or 1/3 of L on the other side. Right? So 1/3 or 2/3 of L. So that is the centroidal location of my triangle. Right? So this is how you can convert this to a point load. Right? Whenever you have a UDL like this. So this application is your dam. Whenever you look after a dam, so you have this uniformly varying load. So how it is? It is like, let me consider. This is my. I am concentrating on a dam like this. Right. So this is my water level. So let me consider this is my cross section of my dam. This is my dam. This is my water level. You know that. So the pressure increases. Pressure increases when you go deeper into the water. Right. So in that case, what happens? You can able to see that your pressure is 0 at this location. The pressure is 0 at this location, but higher pressure at this location. Right? A uniformly varying load like this. Right, in your dam. So that's why your dam is not constructed like this actually. Right, your dam will be like this. Right, you can able to see. So if you go for any Betur dam or something like that, you can able to see the cross section. Your cross section is increasing. Base கீழே பேஸ் வந்து ரொம்ப பெருசா இருக்கும். மேலதான் வந்து சின்னதா அப்படி வச்சிருப்பாங்க. பட் பேஸ் வந்து பாத்தீங்கன்னா நல்லா இன்க்ரீஸ் ஆகிட்டே இருக்கும். Why it is increased? Because the pressure is higher down the sea, right? So whenever you go deeper into the water, so in that case your cross section will be like this, right? That is one of the application of this dam, right? Yeah. So this is the construction of a dam. How it is indicated. So this is WL by 2. We are acting at 2 by 3L and L by 2. Right. So, right. Next, different types of beams. So when you look after the beam, there are 5 different types of beams you can able to see here, which is indicated. So fixed beam, cantilever beam, simply supported beam, overhanging beam, and a continuous beam. Right. These are the different types of beams. Right. So a fixed beam. So you can able to see some slabs in your house. right? So which is fixed on both sides. So fixed on the wall, right? You can keep your whatever cloth or whatever it is, right? So any slabs, right? It is fixed on both the sides. So it's a fixed beam, right? So whenever you have something like this fixed beam, what happens? You will have reactions. You have Rx, you have Ry, and you have moment. Similarly, here also you have Rx, Ry, and moment, right? So this is how it will act, right? Whenever you have a fixed beam, right? So something, this is also a fixed beam, so which is bolted here in all the sides. You can able to see on the other side also. So it will be like a fixed beam. So it is not like fully attaching only through concrete. You can also make a fixed beam by using bolts and nuts, right? These are all fixed beams. Okay, so all bridges you can able to see. Which is a cantilever beam. So you can able to see here in sunshades, right? So in your house, you can have the sunshade. So one side is fixed, other side is free, right? It is free. So for not allowing water to come inside the house during rainy season, right? Or of course, as the name indicates, to avoid sun shades, right? It will give you some shades, right? Something like that. These are all we call it as a cantilever beams. So a lathe is a cantilever type of a beam. So fixed on one side, other is free on the other. Right? If I consider, so there are some lathe like this. Actually, இந்த சைடு ஃபிக்ஸ் ஆயிருக்கும். சில lathe வந்து cantilever lathe இருக்கு. Right? That's simply supported. So something like this. So you can able to see these types of things in temples. So where they won't fix anything, so they will keep the rocks just as it is, right? The design of any locks, something in that locations. So it has two supports. So whatever the rock which will be holding that, that's it. Okay. So this is one type of fixed beam. So something like this. So these are all we call it as a simply supported beams, right? Actually, this is not a simply supported. Actually, only if we consider this two part, it's a simply supported. If you have only two supports, we call it as a simply supported beam, right? Next, overhanging. So you can able to see it has two supports as like a simply supported beam. When I consider up to this part, it's a simply supported beam. But if I extend this as a cantilever, free on other side, then we call that as a overhanging beam, right? So what is the main application here? You have maximum deflection of these types of beams, so that you can easily it will give a spring type of effect, right? So which can be used for jumping, right? So something like that. Next, continuous beam. Whenever you have more than two supports, we call it as a continuous beam. All bridges are continuous beams. You can able to see you have 1, 2, 3, 4, 5, 6, 7, 8 supports. So more than two supports, we call it as a continuous beam.